SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will continue our discussions on air distribution system. In today's lecture we will be covering duct friction chart. We will discuss on the duct friction chart, air duct design criteria, static regain phenomena, dynamic pressure loss in the ducts and method to size ducts. In connection with the air distribution system, last time we discussed the duct design charts. In these charts on the x-axis is a log scale chart. It is known as duct friction chart on a log scale. So starting from 20, then it is going to be 2000. This is 2000, then 20,000 and then 2 lakh. Similarly, starting from here 0.1 Pascal, then it is going to be 1 Pascal, 10 Pascal and 100 Pascal. This is Pascal per meter. Right, and on x-axis it is liters per second. So definitely the horizontal lines, they show the constant duct friction. Now this is 10 Pascal, not 100 Pascal. So 1, 10, 100. Okay. Now these horizontal lines are constant duct friction lines and vertical lines are constant discharge lines. Now these charts, duct friction charts, they have some inclined lines also. They are known as constant diameter lines. Here diameter is equal to constant. Perpendicular to these lines are constant velocity lines. So towards this the velocity is equal to constant. So in these charts now we have all characteristic lines. Now horizontal lines for pressure drop, Pascal per meter, vertical lines for discharge, which is given in liters per second. There are inclined lines, right? They are constant velocity lines, velocity is increasing in this direction, and there are another set of inclined lines which are constant diameter line when diameter is increasing in this direction. Suppose I want to maintain constant discharge, 200 liters per second, right? At 200 liters per second, if I am reducing the duct diameter, because in this direction the duct diameter is reducing. So when the duct diameter, for example, for a particular discharge, this is the duct diameter. If I reduce the duct diameter for the same discharge, velocity will increase, and because velocity is increasing in this direction. So these are constant velocity lines. So for example, for this the velocity is 2 meter per second, for this it may be 5 meter per second, for another line it may be 10 meter per second. They are all assumed values. So velocity is increasing this direction. So the moment we are reducing the duct diameter, the velocity is increasing. But we should bear in mind, the moment the velocity in the duct is increased, the noise level in the duct will also increase. So that has to be taken care of while designing a duct. Now if I am moving in a horizontal direction, suppose I am moving in a horizontal direction, in that case starting from 2000 LPM towards 20,000 LPM, in that case duct friction is remaining constant, but at the same time duct diameter is increasing. That is obvious. For same friction loss, if I want to have more discharge, definitely the duct diameter will increase. And at the same time, it is going to affect the velocity also. So the both, if I want to maintain constant pressure drop, friction pressure drop, then the diameter of the duct and velocity as well will increase. So this is how we can move on this duct friction chart. If two properties are known, suppose I know the discharge and I know the velocity. In that case, other things like friction pressure drop and diameter of duct can be easily calculated like any other chart. Now, before we move on this chart, we should understand the flow in a duct. Now, in order to understand the flow in a duct, it will start with Bernoulli's equation. Bernoulli equation says that P by rho plus half V square plus GZ is equal to 0. So, not 0, it is constant, some constant, or P plus half rho V square plus rho GZ is some constant, let us say K. This P is taken as static head. This half rho V square, this is the kinetic energy of the air, it is known as dynamic head or PS plus PV, and this is potential head, and sum of these all pressures is constant. Normally in the duct design, if the duct is horizontal, then there is no change in potential energy. Even if there is a change in potential energy, it is not very significant. So it is often neglected. Normally for the flow through a duct, static pressure plus dynamic pressure, they are assumed to be constant. This is an ideal condition. This is an ideal condition where suppose there is a diverging section. There is a diverging section. Now state 1 and state 2. So in diverging section, PS1 plus PV1 is equal to PS2 plus PV2, provided there is no friction pressure drop, right? But in actual duct, there is a fan also, which circulates air in the duct, which is known as air handling unit. And due to this fan total pressure, FTP shall also be added here. So PS1 plus PV1 plus fan total pressure is equal to PS2 plus PV2 plus this friction pressure drop, that is PD, pressure drop in friction, PDF, right. So this is the equation for the flow in a duct having a fan arrangement. Now there is an air movement, there is no fan, and there is a movement of air in a section. In a movement of air in a section, then we can always say that P1 P1S plus PS1 plus PV1 is equal to PS2 plus PV2. Now static head at 1, dynamic head at 1 is equal to static head at 2 and dynamic head at 2. If this diverging section, the angle of this diverging section theta is less than 20, it is assumed that, because in this case you can easily find, if you use the continuity equation, rho 1 A1 V1 is equal to rho 2 A2 V2. So you can find that V2 is less than V1, or the velocity of air has reduced and this is known as loss in dynamic head. Now, in this case, this loss of dynamic head will be converted into gain in static head. That is why it is known as static gain during the flow through the duct. So, PS1 plus PV1, this is the equation, PS2 plus PV2. So, PS2 minus PS1 is equal to PV1 minus PV2, right? And this is totally converted into this static head, and the situation is there when it is not totally converted into static head. Now, change in static head is equal to change in dynamic head. Or we can say that whatever drop is there in dynamic head is coming into the gain in static head, but that is the case when theta is less than 20, or diverging this section is this semi vertex angle of diverging section is less than 20 degree. If it is more than 20 degree, then this will not hold true, and static regain is going to be, has to be multiplied by a factor R, which is known as static regain factor, It means some losses will be there. So, this R is less than 1. So, change in static head due to change in dynamic head has to be, this change in dynamic head has to be multiplied by the static regain factor, and only then we will get the static regain. Now, further in a duct flow with friction loss, during this flow there is a friction loss, right? And friction loss, if you take friction losses into the account, then delta P along the length, so L. So, delta PL is equal to total pressure at 1 minus total pressure at 2. The total pressure at state 1 minus total pressure at state 2 will give you the pressure loss during flow in the duct. Now, PT1 is PS1 plus PV1, and PT2 is PS2 plus PV2. Now, if we rearrange these values, then we get PV1 minus PV2 minus PS2 minus PS1. Now, PS2 minus PS1, it means static pressure at state 2 minus static pressure at state 1. It can always be expressed in terms of V1 and V2, and that is equal to PV1 minus PV2, this multiplied by static regain factor R from here, and we get PV1 minus PV2. So, friction pressure loss delta PL can be written as 1 minus R PV1 minus PV2. It means if I know the velocity at state 1 and velocity at state 2, static regain factor is with me, I will get the pressure loss. Now, this value of R is different for different geometries, and this method, this property is used while designing a duct system when we will use the static regains. Now, I will go back to the duct friction chart, actual duct friction chart. In this duct friction chart, this is the actual duct friction chart prepared for a round duct, circular round duct, air density 1.2 kg per meter cube, and the friction, the roughness of the duct is 0.09 mm. Now, this duct friction chart no correction is needed in this, the values getting out of this dust friction chart, when the duct material with a medium or a smooth roughness factor is used and temperature variation is plus minus 15 Kelvin from 20 degrees centigrade or elevation up to 500 meters. So, corrections are not required even if we use this chart to a elevation of 500 meters. Now, here in this duct chart, now they are real values. I explained you earlier with a sketch. Now, this is the actual duct friction chart taken from Extra Handbook of Fundamental 2013. On x-axis, the flow rate is varying from 20 to 2 lakhs, the same value, I mean on a log scale. Y-axis, the pressure is varying, pressure loss per meter varying from 0.1 to 100 pascals per meter. There are inclined lines which are showing the change in duct diameter from 50 millimeters to 3150 millimeters, and there are lines which are showing the duct air velocity starting from 1.2 meters per second to 30 meter per second. Suppose I want to design a rectangular duct. What should I do? Here, diameter of the duct is given as D. I want to design a rectangular duct, and you must have seen a number of rectangular ducts, and diameter of equivalent circular duct is expressed in terms of 1.3 AB raised to power 0.625 divided by A plus B raised to power 0.25. This is A and this is B. Now, in order to find this, because friction loss we assume in both the cases are same, whether it is a rectangular duct or a circular duct, friction loss per meter length is same, because friction loss per meter length is directly reflected in power consumed by the fans. We will use different methods. There are different methods for duct design. So, first of all, guidelines for air duct design. Air should be conveyed as directly as possible, avoid sudden change in direction and cross section. It is obvious. If there is change in inertia, pressure, there is going to be loss of velocity head, dynamic head, and this has to be avoided. If there is a sudden change, the loss will be more. Suppose there is a sudden enlargement in the area. Suppose there is a sudden enlargement in the area. There is a flow in this direction and there is sudden enlargement, right? This is section 1, this is section 2. Definitely when air will enter from this side, it will not immediately move in this direction. Okay, it will take certain curvature and EDs will be formed in this zone and losses will take place. Now, dynamic pressure loss in such a scenario is going to be half rho V1 square 1 minus A1 by A2 whole square. This is going to be the dynamic pressure loss in this case. Remember, if it is diverging with a vertex angle of less than 20 degree, the loss is, all dynamic head will be converted into the static head. But here, the dynamic head loss is going to be this much. If there is a sudden contraction, it means there is an enlarged duct and there is sudden contraction. In this case also, this is state 1, this is state 2. In this case also, there is a Borda-Carnot, this is known as Borda-Carnot equation. So, in this case also there is a Borda-Carnot equation, and that equation says that the pressure loss is rho V1 square A2 by A1 minus 1 whole square. So, these are two Borda-Carnot equations which are used for pressure drop in sudden enlargement and sudden contraction in the duct. So, these type of things are helpful in duct design. Now, there are three methods for duct design. One is variable flow method, another is equal friction method, and third one is static regain method. Now in variable flow method is not a optimum method of duct design. It is more towards the experience of duct designer. In this method, some velocity is assumed, some velocity in the duct is assumed, 5 meter per second, 6 meter per second, that comes from the experience of the designer. And this velocity is known, discharge is known to us. With the help of these two values, we can find the cross section area of the duct and cross section area in different section of the ducts. So the variable flow method is very popular among the design engineers because it requires minimum length of calculations, and but this is not an optimal method of duct design. Another method is equal friction method. In equal friction method, it is assumed that throughout the duct work there is a pressure drop, there is a constant pressure drop per meter length, Pascal per meter. It means, suppose I assume 1 Pascal per meter. So I will be following this line throughout the design of the duct, and throughout the design of the duct, for any discharge I can immediately find the diameter. Suppose discharge is 2000 liters per second, I will draw, it is a constant pressure drop, immediately I can locate the diameter. If the discharge is 10,000, immediately I can locate the diameter, it is approximately 1050. If the discharge is 500, I can immediately locate the diameter, it is approximately 350 millimeters, 350 millimeters. So in equal friction method, in all branches of ductwork, suppose there is a duct network, there is a fan and one outlet is here, A, another outlet is B is here, third outlet C is here. We can have further, we can have outlets like this, D, and then we can have E, and throughout the system, there is a constant friction pressure loss, and then we calculate how much air has been and then we decide the diameter of the different section of the ducts. Now here what happens, suppose if you take this discharge from here, so pressure drop from between these 2 points, absolute pressure drop in Pascal will be less than the pressure drop between this and the farthest point. So in that case what happens, there is an imbalance of airflow, and it is possible that air flow from B is much higher than the required value and we do not get any air flow outlet at D, airflow at D outlet. So in order to control this, dampers are provided at all the openings. Now dampers in a duct, dampers are nothing but they are like a window. If a damper is open, then there is a, if it is 100% open, then it is all right, but if it is partially open, then there is a pressure drop across the damper, and this pressure drop, additional pressure drop compensate the pressure difference between this point and this point. So dampers are provided at this is not a very I mean we cannot say it is very energy efficient system, because on the one hand we are increasing the pressure with the help of a fan, on the other side we are diffusing the pressure using dampers, but we have no other choice if we want to balance the system. Same is the case with the variable flow method also. In variable flow method also, because in different part of the duct network the velocity is chosen by the designer, and in this case also, in order to balance the system, ultimately dampers are provided so that there is no imbalance in the system. Now static regain method I have already explained you, and in static regain method the duct network is designed in such a way that static regain in a particular section is sufficient to overcome the friction loss in subsequent section. So this static regain method is used for large duct networks where optimum design is major concern of the designers, And normally for normal small scale duct designs, variable flow method and equal friction methods are used. In the next class, we will solve a numerical on this duct design methods. Then you will have more or clear insight of the duct designing. This is all for today. Thank you very much.